Hello everyone, this is Professor Mahesh Pardeshi from Parvatibai Genba Music College of Engineering, Wagoli, Pune. In the yesterday's lecture, we seen the two properties of the fluid, that is physical properties of fluid. First is the mass density and second one is the weight density. Now today we are starting with the next physical property, that is the specific volume. Specific volume. Now, specific volume of the fluid is defined as the volume of a fluid occupied by unit mass or volume per unit mass of the fluid is called as specific volume. See, as per the definition, mathematically specific volume is expressed as volume of the fluid divided by mass of the fluid. See this expression. See this expression. Specific volume is equal to volume of the fluid divided by mass of the fluid. Volume of the fluid divided by mass of the fluid. Again, we can write this expression as 1 upon mass of the fluid divided by volume of the fluid. This volume of the fluid is get into this denominator as 1 upon mass of the fluid to the volume of the fluid. And you already know this value, this definition: mass of the fluid divided by volume of the fluid. Mass of the fluid divided by volume of the fluid is known as mass density, is known as mass density and denoted by rho. Therefore we can write 1 upon rho. Specific volume is equal to 1 upon rho, that is 1 upon mass density. Therefore, thus specific volume is the reciprocal of mass density. Very simple. Specific volume is the reciprocal of mass density. Mass density. Its unit is as the unit of the mass is kg and unit of the volume is meter cube. Density means the unit of the density is kg per meter cube, but it's a reciprocal of mass density. Specific volume is nothing but the reciprocal of mass density. That's why its unit is meter cube per kg, reciprocal of the unit of the mass density, that is meter cube per kg. Here you can see that unit, meter cube per kg. It is commonly applied to gases. See the basic difference between the gases and liquids. Okay. In case of the gases, we use the expression as volume of the fluid divided by mass of the fluid. But in case of the liquids, we have to use the expression as volume of the fluid divided by weight of the fluid. Divided by weight of the fluid. This is the difference between the liquids and gases. In case of the gases, we have to use this expression. In case of the gases, we have to use this expression, that is volume of the fluid divided by mass of the fluid. But in case of the liquids, we have to use volume of the fluid divided by weight of the fluid. Volume of the fluid divided by weight of the fluid, not the mass. Okay. Okay. This is the basic difference between the specific volume of the gases and specific volume of the liquid. All of you get this concept? Okay. Now go to the next property, that is the specific gravity. That is the specific gravity. It is also called as relative density. It is also called as relative density. Now see the definition. Specific gravity is defined as the ratio of weight density or simply density of the fluid to the weight density of the standard fluid. Weight density of standard fluid. Now see First thing, that is standard fluid. What is mean by standard fluid? In this subject, fluid mechanics, many times we have to compare the properties with one reference point, and that reference point is nothing but the standard fluid. Means we have to compare the different properties of the fluids with respect to the standard fluid, and that standard fluid is nothing but the water. That standard fluid we have to use as a water. We have to compare the properties of the oil with respect to water. Means we have to compare the different properties of different types of liquids with respect to water, and water is called as a standard fluid. Now see the definition again. Specific gravity is defined as specific gravity is defined as the ratio of the weight density of the fluid to the weight density of the standard fluid. Weight density of the fluid to the weight density of standard fluid. Here, mathematically you can see here specific gravity for liquids. Specific gravity for liquids. It is the weight density of the liquid divided by weight density of water. We can also write here simply the density of the liquid to the density of water. This expression is also correct because weight density is equal to mass density into G, and here also G we can say. Okay, so we can also write as density of the fluid to the density of water. Specific gravity is equal to weight density of liquid to the weight density of water, or simply the mass density of liquid to the mass density of water. We can also write this. Okay, see the next line. For liquids, the standard fluid is taken as water, and for gases, the standard fluid is taken as air. And in case of gases, the standard fluid is nothing but the air. The specific gravity is also called as the relative density. It is a dimensionless quantity and it is denoted by symbol S. Why it is a dimensionless quantity? Because the same quantities are divided. Means weight density divided by weight density. Unit of the weight density get cancelled because in the numerator and denominator same quantity is there. That's why the unit gets cancelled, and therefore it is a dimensionless quantity. Therefore it is a dimensionless quantity. See, for standard fluid, the specific gravity of the water at the standard temperature is 1. Is 1. That's why we considered it as a standard fluid, because its reference point or its specific gravity is 1 unity. It is very simple to compare between the two liquids because the reference is 1. We can easily compare with others. For example, the specific gravity of the mercury is 13.6. The specific gravity of the mercury is 13.6. We can compare the mercury with water very simply. Very simply. See, mercury is 13.6 times heavier than water. Heavier than water because its specific gravity is 13.6. Its weight is nothing but 13.6 times the weight of water. Its weight is nothing but the 13.6 times more than the weight of the water. Likewise, we can compare every property of the liquids with the reference to the standard fluid, that is the water. Understand? Now, here you can see that the weight density of the liquid is equal to specific gravity into weight density of water. Similarly, I have explained the example of mercury. Same way, mercury specific gravity is 13.6. Specific gravity of Mercury is 30.6. That's why weight density of the Mercury is nothing but the specific gravity into weight density of water, that is 13.6 into 1000 into 9.81 Newton per meter cube. Newton per meter cube. Okay. Okay. Next point. These two properties are also very important, that is the specific volume and the specific gravity. Now we come to the next property, or before going to the next property, these are some values of the specific gravities of the material, different types of liquids. Okay, for water the specific gravity is 1, for blood specific gravity is 1.05. For sweet seawater contains large number of the salts. Seawater contains large number of salts. That's why its specific gravity is not equal to 1. Okay, its specific gravity is 1.025. Okay, gasoline, ethyl alcohol, mercury, wood, gold. Here you can see that the specific gravity of gold is 19.2. For the bones, 1.722. Air, air is 0.0013. Okay, and the example of mercury is given here. You can see here. Specific gravity of mercury is 13.6 and the density of the mercury is 13.6 into density of water. This is the density of water, that is weight density of the mercury is 13,600. Okay, now next property is the viscosity. It is the very much important property and used many times, many places, and there are some problems based on this property, viscosity. It is very important property. Now see the definition of viscosity. Viscosity Viscosity is defined as the property of the fluid which offers resistance to the movement of one layer of the fluid over the another adjacent layer of the fluid. It is the property of the fluid which offers resistance. This is very important word, resistance. Viscosity is nothing but the resistance to the movement of one layer of the fluid over the another adjacent layer of the fluid. Okay, this viscosity we can explain by using this diagram. Okay, here when the two adjacent layer of the fluid a distance dy apart moves one over the other dy. This distance dy means these two layers are this dy distance apart. Okay, at different velocities, say u and u plus du. Here the velocity of the first layer is u and the velocity of the layer just above this layer is u plus du. Change in the velocity with respect to dy distance is du. Du is nothing but the change in the velocity with respect to this distance dy, small distance dy. Okay, and this du is also a small change in velocity, very small change. Okay, as shown in figure. The viscosity together with the sorry the viscosity together with the relative velocity cause a shear stress cause a shear stress acting between the fluid layer. See what happens, the velocity of this first layer is less and velocity of this adjacent above layer is more. Why it is so happens? Why it is so happens? See, this is the velocity profile. Here you can see that this is the velocity profile. This is the bottom or a datum part. Suppose this is a river flowing into this direction, river flowing into this direction, and this is the bottom layer, or this is the datum of the river, base part of the river. When the water is flowing through this direction, when water is flowing from this direction, at this part, at this part, there is no movement of the water. There is No moment of water. No moment. As there is a no moment, there is no velocity. That is here you can see that zero velocity. At this bottommost point you can see here the velocity is zero. And as we move towards upper and upper part, as we move towards the upper part, the velocities goes on increasing. Here you can see velocities goes on increasing. Why it happens? Because there is a movement of water from this direction to this direction. Okay, at the top layer, at the top layer the velocity is maximum. At the top layer the velocity is maximum. Okay, here you can see that you can see that the velocity goes on increasing as we move towards the upper part. Okay, therefore here the velocity of this first layer is u, and the velocity of this upper layer is u plus du, means there is a change in velocity or increase in the velocity with the amount du of the upper layer, and that bottom layer the velocity just only u. Okay, so can you imagine what happens when these velocities are different? What happens? Can you imagine? Due to the higher velocity of this upper layer, due to this higher velocity of this upper layer move, try to move very high speedily than this layer. Okay, this layer is moved with some high velocity than this layer. Then what happens? There is a shear developed between these two layers. There is a shear developed between these two layers, and due to that shear what happens? Due to that shear what happens? There is development of shear stress between these two layers. There is a development of shear stress between these two layers. Between these two layers, there is a formation of shear stress. And the shear stress, what happens due to that shear stress? What happens due to the shear stress? There is a viscosity. There is a viscosity due to that shear stress. There is a viscosity due to the shear stress. What happens? You can see that while we change the distance dy, while we change the distance dy, the change in the velocity is du. Change in the velocity is du, and this change is nothing but the velocity gradient. This du by dy is called as velocity gradient. This du by dy is called as velocity gradient, and due to that velocity gradient there is a shear stress. Due to that velocity gradient there is a shear stress, and due to whole this thing there is a viscosity. Due to this whole thing there is a viscosity. Can you all of you get the idea of this viscosity? Okay, see the definition again. Viscosity is defined as the property of the fluid which offers resistance to the movement of one layer of the fluid over the another adjacent layer of the fluid. Means due to this variation, due to this du by dy, due to this velocity gradient, this upper part exerts a resistance to this lower part, and lower part exerts a resistance to the upper part. Both of the layers exert a resistance to both of these layers, and this resistance is nothing but the viscosity. This resistance is nothing but the viscosity. Now see mathematically, next part. The two layer cause a shear stress on the adjacent lower layers, while the lower layer causes shear stress on the adjacent top layer. Means both layer apply a shear stress on each other. Okay. This shear stress is proportional to the rate of change of velocity with respect to y. It is denoted by symbol tau, called as tau. Mathematically, shear stress. This tau is nothing but the shear stress. Tau is nothing but the shear stress, and this shear stress is directly proportional to velocity gradient. Directly proportional to the velocity gradient. This du by dy is called as velocity gradient. See, this du by dy means change in the velocity with respect to dy, y direction or y displacement is called as is called as velocity gradient. And here stress is directly proportional to the velocity gradient. So we can use this formula as tau is equal to mu into du by dy. Tau is equal to mu into du by dy. This mu is the proportionality constant. This mu is the proportionality constant, and this is called as dynamic viscosity. This mu is called as dynamic viscosity. This is very important equation we have to use many times while solving the problems. That is tau is equal to mu into du by dy. This mu is called as dynamic viscosity. This mu is called as dynamic viscosity. Can you find the dynamic viscosity from this equation? Very simple. Just divide by this du by dy to this tau. We will get the dynamic viscosity very easily. Therefore, dynamic viscosity is equal to shear stress, that is tau, divided by du by dy. All of you get this? All of you get this? Mathematically, the shear stress is denoted by this velocity gradient. Shear stress is directly proportional to this velocity gradient, and this mu is nothing but the constant of proportionality, and that mu is called as dynamic viscosity. See the next point, where mu is called as the constant of proportionality, and it is known as coefficient of dynamic viscosity, or just only the viscosity. Okay, du by dy represent the rate of shear strain or the rate of shear deformation, or just simply the velocity gradient. This du by dy is called as velocity gradient. Here you can find the dynamic viscosity by using this equation. I already told you dynamic viscosity is equal to tau divided by du by dy. This equation we can also use for solving the problems many times. Okay. Thus, the viscosity is also defined as shear stress required to produce the unit rate of shear strain. Unit rate of shear strain means this velocity gradient. Rate of shear strain is called as velocity gradient. Viscosity is simply the ratio of shear stress to the velocity gradient. Got it? Now, next point is unit of viscosity. Next point is the unit of viscosity. The unit of viscosity is obtained by putting the dimension of the quantities in equation. Very simple. So, first of all, we have to put the unit of this stress. All of you very well know about this stress. In strength of the material, you solve many problems based on this stress. And what is the definition of stress? Stress is nothing but the force upon area. Normal force to the cross-sectional area is called as stress. Stress simply denoted by force upon area. Now here, change in the velocity divided by change in the distance. What is the unit of velocity? What is the unit of velocity? Velocity is nothing but the distance upon time. Velocity is nothing but the distance upon time, that is meter per second. And also here the unit of distance is meter. Length, here you can see that length divided by time into 1 upon length. Okay, got it? Now here finally we will get the unit of viscosity as force into time divided by length. By solving this all the things, we will get force into time divided by length square. Length square comes from this area, length into length. This length cancel. This length cancel. This time goes to the numerator and this area to the denominator, and the area the unit of the area is length square or meter square, and the time is taken here from. Okay, so unit of the viscosity is, here you can see that Newton second per meter square. Newton second per meter square. The unit of this force is Newton, unit of this time is second, and unit of this length is meter. Therefore, finally we get the unit as Newton second per meter square. Newton second per meter square. This is the SI unit of viscosity. or it is also called as dynamic viscosity. SI unit of dynamic viscosity is Newton second per meter square. Now, next point, it is also very important point, that is kinematic viscosity. It is the kinematic viscosity. Okay, it is defined as the ratio between the dynamic viscosity and the density of the fluid. Very simple point, very simple definition. It is the ratio between dynamic viscosity to the density of the fluid. Here mathematically you can see here it is denoted by mu. It is denoted by mu. It is denoted by mu. Dynamic viscosity is denoted by mu. Here you can see that dynamic viscosity is denoted by mu, and the kinematic viscosity is denoted by mu. Kinematic viscosity is denoted by mu. And mathematically you can see here mu is equal to, or kinematic viscosity is equal to, dynamic viscosity divided by density. Dynamic viscosity divided by density. It is equal to mu divided by rho. Mu divided by rho. The SI unit of kinematic viscosity is meter square per second. Meter square per second. This you can get very easy. Just put here the, here you have to put the unit of the dynamic viscosity, that is, here you can put Newton second per meter square. Newton second per meter square, and here you can put the unit of the density, and that is Newton per meter cube. That is Newton per meter cube. You will get, finally get this value, meter square per second. Meter square per second. You can take out. You can take out. Okay. Now, next point, that is Newton's law of viscosity. Newton's law of viscosity. It states that the shear stress tau on the fluid element layer is directly proportional to the rate of shear strain. Newton's law of viscosity said that states that the shear stress is directly proportional to the rate of shear strain. Shear stress is directly proportional to the rate of shear strain. The constant of proportionality is called as coefficient of viscosity, and mathematically it is expressed as given by the formula or equation 1.2. We already seen it in case of dynamic viscosity. Here, this equation. Shear stress is directly proportional to shear strain. Here you can see that shear stress is directly proportional to the shear strain or rate of shear strain. It is also called as velocity gradient. And here mu is the constant of proportionality. Shear stress is directly proportional to shear strain or rate of shear strain. It is also called as velocity gradient, and constant of proportionality is mu. Constant of proportionality is mu. So this is the Newton's law of viscosity. This is the Newton's law of viscosity. Okay. This is the last point of today's lecture. That is the Newton's law of viscosity. Today we see the four properties of the fluid. First property is specific volume. Second property is specific gravity. Third property is dynamic viscosity. And fourth property is kinematic viscosity. Thank you.